y'all, welcome back to another round of chemistry notes. In this video, we're going to talk about states of matter, classifying matter, and how to separate the different types of matter. So the first thing we need to do here is talk about our states of matter. Those are going to be, of course, solid, liquid, and gas. We're going to talk about the different properties of each one and how they compare to each other. So let's start with volume and shape. Your solids have a definite volume and shape. The volume and shape do not depend on the container. So an example of this would be something like, I don't know, your cell phone, right? Your good old cell phone, it goes with you everywhere. And it doesn't matter where you put your cell phone. It doesn't matter if it's in your pocket or in your bag or on your desk or anywhere you keep your cell phone. It's not going to change its size or its shape. It's my beautiful cell phone picture. It's always the same size and shape. It's still cell phone shaped. But if you compare this to a liquid, something like water, water has a definite volume. Liquids have a definite volume, just like solids, but they take the shape of their container. So if you've ever baked or cooked something that asks you to measure out, say, a quarter cup of water, then you're going to take your measuring cup and you're going to fill it with a quarter cup of water, and then you're going to pour it into a bowl or a dish or something. And the water will start out measuring cup shaped and it'll end up bowl shaped, but it'll still be the same amount of water. It'll still be the same volume. So the volume change stays the same, even if the shape changes. And then if we compare this to a gas, gases assume the shape and volume of their containers. So if you think about something like a can of, I don't know, Febreze or some other room spray, you have your little can, and it starts out in the can. It's the size of the can, it's the shape of the can, all of your little gas particles are in this can, so they are can shaped. But as soon as you start to spray that can, those particles, that gas is gonna exit the can and it'll start to spread out and it'll fill up your whole room. It'll take the size of your room and the shape of your room, and you'll be able to smell it in every corner of the room because that gas is taking the shape and volume of the room. It started can shape and size, and now it's room shape and size. As those particles spread, those particles are going to move in a specific way as they are spreading out. Your cell phone particles and your water particles and your Febreze particles all have different amounts of kinetic energy. And kinetic energy has to do with movement. So more kinetic energy, more movement, less kinetic energy, less movement. Your solids, your cell phone, when you're looking at it, it just sits there. It's not like vibrating. There aren't waves going through it. Solid particles have relatively low kinetic energy. The only movement is for those particles to vibrate in place. They're not moving around. They're all organized in these blocks and they can't go anywhere. So this particle might shift a tiny bit this way and a tiny bit in each direction, but it's just shifting around in place. It's just kind of shivering. It's not actually traveling in space. Compare this to your liquids. These have a medium amount of kinetic energy, because the particles can sort of slip and slide past each other, but they're not moving too far and they're not moving too fast. So these particles can move around a little bit, but they're still packed in pretty close. So they're not just freely traveling, they're just sort of scooching past each other. And then last we have our gases. These have a pretty high kinetic energy. We're going to spend an entire unit talking about gases and their kinetic energy and how they move. But if you look in your picture up here, you actually have motion lines of your gases traveling because they're moving a lot. These particles are zipping around really, really fast. It's like if you took a toddler and got them hyped up on sugar and then just set them free. These gas particles are racing around the room really quickly and without a whole lot of order, which is the next thing we're going to talk about, is the amount of order in each of these states of matter. Gases, we just said, have relatively low order. These particles are not paying attention to where they are or where they're going. They're hyperactive small children, and they're just racing around, bouncing off of stuff any which way. Your liquids, on the other hand, have a medium amount of order. They're a little more organized than your gases, but they're still, it's not like single file lines. They're not super organized, so it's moderate. And then you have your solids, which are in single file lines. They're in nice, neat little rows, in columns, in these really organized shapes. Solids have a relatively high amount of order. Those particles are organized. The next thing we need to talk about is rate of diffusion. Diffusion is how quickly your particles spread out and move around. So again, think about your cell phone. When you set your cell phone down on the table, it doesn't evaporate. It doesn't disappear because all of its particles have gone different directions. Your solid particles don't spread out. They have a very low rate of diffusion. The particles mix very slowly. Another example here would be to think of pouring sand into a bucket of salt. They might mix a little bit right at the very top. So here's our salt, and we can throw our sand on top here. And maybe some of that sand will get into the salt, maybe some of the salt will get into the sand, but for the most part, you're just gonna keep your two separate layers and they're not really gonna mix because they have a very low rate of diffusion. Liquids, you might pick up a trend here, liquids have a medium, a moderate rate of diffusion. The particles mix easily, not super duper quickly, but pretty easily, a lot easier than your bucket of salt. So think of mixing milk into coffee, right? You take your cup of coffee and you pour some milk into it and it does that cloud swirling kind of thing, and it'll eventually mix itself up without you even having to touch it. Might take a minute, but it'll do it itself. And then last we have our gases, which have a relatively high rate of diffusion. Particles mix very quickly. So think of something like Axe body spray. If someone were to spray Axe body spray in one corner of the room, it would not take you very long to be able to smell it from the other room. It would not take you very long to smell it from the other corner of the room or a completely different room, because those gas particles spread out and diffuse really, really quickly. So, and that again comes from this kinetic energy. These particles are moving faster, so they're gonna travel farther. They're moving around, they're not organized, they can get everywhere. Versus your solids are very organized, they're not moving very much, so of course they're not gonna spread out and diffuse. The next topic we're gonna look at here is density. So density has to do with mass and volume, right? We all learned in middle school that density is equal to mass over volume. We also learned this earlier this year. So if you have a high mass in a little volume, a big number on top and a little number on the bottom, that's going to be a relatively high density. Another way to think of density is just how tightly those particles are packed in together. And if we look back up at our picture, these particles are packed really tightly in together. There's really not a whole lot of room to spare in between them. Your liquids have, once again, a medium density. They have a medium mass for the volume they're in. Looking at our picture, they're a little more spread out. There are tons of particles in our solid. There are a medium number of particles in our liquid taking up the same amount of space. So a little less mass in the same amount of volume. And then your gases have a very small mass in their large volume. They have a relatively low density. And this again comes from the fact that they're not organized and they're flying around everywhere really quickly, so there's a lot of space between them. In any given space, there are not that many actual gas particles. So here we've got 4 particles, here we've got maybe something like 30, here we probably have hundreds of particles. So the closer they're jammed together, the more mass you have in space, the higher the density. Last two, these sort of go hand in hand. Since our gases are very, very spread out and there's tons of room between the particles, they have a pretty high level of compressibility. They are easily squished. If we look back up at our picture, if we could grab onto one of these particles as they're moving around, it would be really easy to just grab this one and squish them together because of all this empty space between them. They're easy to squish. Liquids have a little bit of empty space between them, but not nearly as much as the gases. So your liquids are barely compressible. They have just a tiny bit of extra room to squish together. So they're relatively incompressible. You can do it a little bit. You can squish them just a bit, but for the most part, they are incompressible. You can squish them a little, but enough pressure is just going to turn them into a solid. And then your solids, there's no room between these particles. They're all touching. There's literally nowhere for them to go. So your solids are incompressible. They cannot be squished. If you try to squish a solid, best case, nothing will happen. Worst case, you're going to break it because there's no room for those particles to go. And last but not least, the reason that these particles behave the way they do has to do with the attractive forces between them. The attractive forces are like little magnets that hold the particles together. So solids have really strong attractive forces holding their particles together. That's why they're all lined up next to each other. They're all touching. They're also stuck and not moving because there's really strong forces holding them together. So of course they can't go anywhere. Your liquids are a little more spread out. Those particles can move around a little bit more. And it's because their attractive forces are not quite as strong. They're a sort of a medium level of attractive forces. So this is a medium level. And your gases, if you take a look at this picture, these particles are not interacting. They're just completely ignoring each other. Remember, we talked about them being like hyped up little kids on sugar? Those little kids are not going to interact. They're just going to race around the room. They might run into each other occasionally, but they're just busy doing their thing because they're not interacting at all. They're too high energy. So that's going to be very low attractive forces between our gas particles. All right, so now that we have talked about our different states of matter, let's talk about just a couple more properties of them. So to talk about compressibility just one more time, because this is probably one of the less familiar aspects of what we just talked about, we've got 3 levels of compressibility here. On the left-hand side, we've got something that's squished a lot. It started out with a pretty large volume and it ended with a very small volume because it squished a lot. This thing here was highly compressible. And the state of matter that we talked about being highly compressible was a gas. Here on the other end, we've got something that didn't squish at all, right? It started with this volume and it ended with this volume. And if it cannot be squished, if it is incompressible, it must be a solid. The volume didn't change at all. We couldn't squish it. And here in the middle, it compressed just the teensiest bit. It started with this volume and it ended with one just the tiniest bit smaller. So that's going to be barely compressible, which must be our liquid. So gases, highly, solids, completely incompressible, and liquids, sort of in the middle. To get between our different phases, we have our different phase changes, which again, you've probably learned several times before. But what you might not have talked about is how they happen. Because to change between your different states of matter, to undergo a phase change, you need to either absorb energy or release energy, right? These things don't just happen. You've got to cause them. You've got to put energy in the form generally of heat, or you have to take energy out. So the types of changes that require absorbing energy, well, those are the things that get warmer. So your melting process, which is from a solid to a liquid, right? You heat that up, you put energy in, and it melts. Or going from a liquid to a gas, you put some water on the stove and you can boil it. It'll vaporize. You might be used to calling it evaporation. We're going to call it vaporization in this class. Evaporation is a special type of vaporization. But if you can remember this one, evaporation, it's got this word vapor in the middle. And the word you need to remember starts with vapor. So if you can remember this, it's not too much of a leap to get here. And another one that you may have learned about but might not remember, it is possible to go straight from a solid directly to a gas. You don't have to pass through liquid. This is called sublimation. When you go straight from a solid to a gas, you don't pass through liquid at all. It's called sublimation. An example of this would be dry ice. Dry ice is solid carbon dioxide. It's the solid form of CO2. And when you put it out on your counter or, whatever you're using dry ice for, it doesn't melt into a puddle of carbon dioxide. It goes directly, turns into a gas of carbon dioxide. When you see that fog, that smoke coming off of it, that's actually water in the air being affected by this process of sublimation. So straight from a solid to a gas, that is sublimation. Clean this up for ourselves a little bit. We can also go the other way. The other half of these processes require you to release energy. These things need to cool off. They've got to get rid of energy. So that would be an example of going from a liquid to a solid, right? You fill an ice cube tray with some water, throw it in your freezer, and it freezes from a liquid to a solid. That process requires the water to get rid of some energy. Another example would be from a gas to a liquid. You might have seen this happening if you've ever had a cold glass of water, of some ice water on a really hot day, and the outside of that glass starts to get wet. It gets covered in water, and that's not water leaking through the glass. It's water vapor from the air condensing on the side of your cold glass because it's getting rid of some energy, and now it can condense onto the glass. And again, probably the least familiar of these three is from a gas directly to a solid. So this would be called deposition. And this is a pretty rare one. We really don't see this very often. It is how they make dry ice. They take gaseous CO2 and deposit it directly into a solid form of CO2. So again, the cooling down kind of processes require you to release energy, and the heating up kind of processes require you to absorb energy. All right, now that we've talked about our different states of matter, we're going to talk about how to classify it, because matter is a really big umbrella term. Matter is anything that has mass and occupies space. Everything we know in the universe is either energy, which is going to get its own unit pretty soon, or it's mass. Anything you've ever smelt, anything you've ever touched or tasted or felt, that is matter. So we break it down into some smaller groupings to make it easier to talk about, and we do that according to its composition, which is just the basic pieces that make it up. What is it made of? All matter is either a pure substance or a mixture of substances. Basically, it's either made of one type of thing or it's made of a lot of types of things. Those are your options. So first we'll talk about pure substances. These have a fixed composition. They're made of one type of thing. They are fixed and they cannot be separated by physical means. If you want to split up a pure substance, you better bring something pretty impressive because you're not going to be able to just filter them apart. Within our pure substances, we have two types. There are elements, and an element is a pure substance that's made of just one type of atom. You can find a complete list of your elements on the periodic table. If it shows up on the periodic table, it's an element. If it does not show up on the periodic table, it is not an element. Or it's an element that hasn't been discovered, but probably it's just not an element. So some examples would be boron, which is B, or tungsten, which is W, or oxygen, which is O2. More on this pretty soon, but oxygen is actually made of two oxygen atoms stuck together. It's still an element though because both of those atoms are oxygen. It's still just one type of atom. Your other option is a compound. And a compound is still a pure substance, but it's made of two or more elements in a fixed proportion. So examples would be water. Anytime you have water, no matter how big or how small the sample, there will always be two hydrogens and one oxygen. You will never get a ratio besides that. Another example would be glucose. It's what your body uses for energy. And you will never have a sample of glucose that has any other combination of elements besides 6 carbons, 12 hydrogens, and 6 oxygens. They always show up in that exact same amount. Or my personal favorite compound, caffeine, you will always get 8 carbons, 10 hydrogens, 4 nitrogens, 2 oxygens. They are in a fixed proportion. You will never get a different ratio than that ratio because they are pure, they are a compound. On the other side of our types of matter, we have our mixtures. And a mixture is a blend of two or more kinds of matter. Notice this is not two or more elements, this is two or more kinds of matter. Within this, each type of matter maintains its own identity and properties. Back here, when we were talking about our pure substances, when we make a compound out of carbon and hydrogen and oxygen, if we arrange them specifically in this ratio, they stop acting like carbon and hydrogen and oxygen and they start acting like glucose. They give up their own properties to be part of this compound. In your mixtures, if you just mix together carbon and hydrogen and oxygen in a mixture, in a physical blend, each one is going to keep its own identity. This will still act like carbon, this will still act like hydrogen, and this will still act like oxygen. Because they're just physically blended together, they can be separated by physical means. We're going to talk about those physical means at the very end of these notes. So just like our pure substances, our mixtures have two types. There are homogeneous mixtures. You might also hear this pronounced homogeneous. Both are acceptable. And this contains two or more substances blended evenly. So this prefix, homo, means same. And these are called homogeneous or homogeneous mixtures because they look the same everywhere. These are also called solutions. Examples of this would be taking chocolate powder and dissolving it into milk to make chocolate milk or hot chocolate, right? You start with your completely just smooth white milk and you have your crystally chocolate powder. You dump it in there, stir it up really good, and when it's done, you can't look at it, assuming you've done it correctly, you can't look at it and say, oh, this is chocolate powder and this is milk, and I can see the two separate pieces. It just looks all the same throughout. Or Gatorade, which is largely water, but it also contains sugar and electrolytes, which we're going to spend a whole lot of time talking about, and dyes and preservatives and flavors. But you can't look at a bottle of Gatorade and say, oh, there's the water and there's the sugar and there's the sodium and there's the potassium. It just looks the same all throughout. It's all one even blended solution. Another pretty cool example is brass, which is a combination of the metals copper and zinc. So a lot of different things are made of brass. You've probably seen examples in your home, or if you've ever seen a trumpet or a trombone or any brass instrument, they are made of brass. Someone took a big chunk of copper and they melted it. They took a big chunk of zinc and they melted it, and they mixed these two together super, super thoroughly. They mixed them up really, really well, and then they formed them into the shape that they wanted them to be and let it harden. And when that's done, you cannot look at your trombone and say, oh, there's the copper and there's the zinc. I see it now. It all looks exactly the same throughout because it is homogeneous. It is the same. The other side of this is a heterogeneous mixture. This prefix hetero meaning different. So these are mixtures that look different throughout. When you look at them, you can see the different pieces because they're not blended evenly. The different parts are easily distinguishable. So if you've ever had a vinaigrette salad dressing made of oil and vinegar, or even oil and water, these things don't mix. You might have heard, oh, they mix like oil and water. It's because they don't mix. And you can shake it up as much as you want to. You could put it in a blender and blend it, but if you look, you're still going to see little pockets of oil floating around in your vinegar or in your water. You're going to see the different pieces. You can say, oh, this is the oil and this is the vinegar or the water or whatever you're mixing it in. Another example would be an iced drink. Not a cold drink, but an actual drink with ice cubes in it. Looks a lot like the cell phone. So if this was tea, you could look at the glass and say, oh, this is tea and these are ice cubes. I can see the different pieces of this mixture. Or a pepperoni pizza. You can say this is cheese and this is pepperoni. You can see the different pieces. They're easily distinguishable because they look different throughout. So here's a nice flow chart for you to sort of help you travel through this. We start at the top with all matter, and you ask yourself, is there a variable composition? If the answer is no, it is the exact same thing everywhere I look, it's always made of the exact same combination of things, then it's a pure substance. Then it's either an element made of all one type of atom, like helium, or it's a compound made of more than one type of atom, but always in the exact same fixed amount. I can take a chunk out of any portion of this picture, and that chunk will always have a ratio, since it's water, of 2 hydrogens to 1 oxygen. It does not matter where I pick it up, it's always going to have this ratio. If it has a varying composition, if it's not the same everywhere, it's a mixture. It's either heterogeneous, where you can see the different pieces. This is wet sand, and I can clearly see, here's the water, here's the sand. I can see my different pieces. Or it's your homogeneous, your homogeneous mixture, your solution, which looks the same everywhere, but when you get down on a microscopic level, it's different from a compound. These are the two that I think people tend to get confused the most. But again, if I took a sample from anywhere in my water, it's always 1, 2, 3, 4, 5, 6, 7, 8 hydrogens to 1, 2, 3, 4 oxygens. Always that exact same ratio. But over here in my solution, I could take a sample from right here and it's all water. And I could take a sample from right here and that's just sugar. Those samples are not the same thing because this has a variable composition. From a distance, it all looks the same, but up close, it looks different. Here, it doesn't matter if it's from a distance or up close, it looks the same everywhere. All right, so now you've got some practice in your book to help you sort of distinguish between your different types. Take a second, work through this, try to label each of those pictures as either an element, a compound, or a mixture. You don't have to say which type of mixture because when you're zoomed in super close, it's sort of hard to tell what type of mixture. But element, compound, or mixture, and explain how you know. When you're ready, unpause the video and check your work. All right, hopefully this is what you came up with. Again, these first two are both elements because they are all one type of atom. This is it. The only atom here is the purple atom. The only atom here is the yellow atom. So these are elements. Down here, we had a compound because it doesn't matter what portion of this thing I pick up, I'm always going to have the same proportion of 3 blue atoms to 1 gray atom. And then over here, we've just got all kinds of things going on. So this is going to be a mixture because if I take a sample from here and a sample from here, things are not present in the same amounts. It is varying in its composition. It is a mixture. Based on what we're seeing here, it's hard to say whether it is a homogeneous or heterogeneous mixture, but we know for sure that it's not a pure substance. And here's what you should have gotten for question number 2 and those different substances. All right, last thing, let's talk about how to separate a mixture. Again, this is for mixtures, this is for physical separations. Doesn't matter what type of mixture, either heterogeneous or homogeneous, it can be separated by physical means into its component parts, making it up. Your first method is for separating a solid and a liquid, and that can be done by pouring your mixture through a filter paper that is designed to allow only the liquid to pass. So here we've got a mixture of solid and liquid, maybe something like sand and water. If we pour our mixture through this funnel with the filter paper, the paper is going to catch the solid and just the liquid will pass through. Now we've got solid up top and liquid in the bottom, and we have separated them. So that's the simplest way to separate a solid and a liquid. Notice that this probably works best for your heterogeneous mixtures because you have to be able to see the different pieces in order for one to get caught in the filter and the other to not. Our next method will work for homogeneous mixtures. Specifically homogeneous mixtures of liquids. They can be separated using a process called distillation. which is when you take your mixture of liquids and you put them in a flask, and then you heat that flask over a Bunsen burner or a hot plate, and they're both going to heat up. But the one that has a lower boiling point, the one that is more volatile, is more easily vaporized, one of them's going to boil first. And that vapor it turns into is going to come up the flask. It's going to go down this little arm. And once it enters the arm, it'll start to cool off because this condenser is made for cooling. So that vapor will cool down back into a liquid. It'll flow down this arm and it'll fall into a collection flask. And now you've separated them because the one that boils at a higher temperature, this is the hard one to boil, stays behind in your initial flask, and the one that is easy to boil ends up over here in your collection. So that can help you separate mixtures of liquids when you couldn't just pour it through a filter because everything would go through. And our last method is called paper chromatography. It's probably the prettiest method. Paper chromatography takes advantage of the fact that different components in a mixture, and again, this will work for homogeneous mixtures, have different attractions to a solvent and to paper. So let's say you wanted to separate out the different inks in a black marker or a black pen, because black is a combination of all the colors. They've all got to be in there somewhere. You could put a little ink spot on a special type of paper called chromatography paper, and then dip the end of that paper into some water. And the water is going to travel up this paper as water does. And as it does that, it's going to pick up this ink and kind of smear it up the paper as well. If you've ever written something in pen and then gotten that paper wet, you might notice that the ink smears, it transfers because it's attracted to the water that is flowing over it. But as this happens, the different colors in that ink are going to be different amounts of attracted to the water and to the paper. So here, this yellow ink was really attracted to the water and only kind of attracted to the paper. So it holds on to that water and it follows it all the way up our chromatography paper. And then our orange ink was only kind of attracted to each one, so it went sort of a middle distance. And then this purple ink down here was really pretty attracted to the paper. It was pretty happy to stay put and only traveled with the water a little bit. So since each component has a different attraction, they're all going to travel different amounts, and you can separate them out that way. So here you've got a chance to practice some more on your different states of matter, how to identify them visually, how to identify them by description, by properties, by behavior. Take a minute, work through the next 6 problems, and when you're ready to check your work, unpause the video. All right, hopefully this is what you ended up with. If you need a little clarification on why these are the answers, go ahead and check out the answer key on my website, and it will walk you through the reasoning on some of these a little more clearly. If you got them all right and you are feeling good, it means it's time to head over to Quest and work on that assignment. Good luck and happy studying.